So hello everyone. Today we will be seeing the lecture 4 of the week 1. So in the last lecture we discussed about the solution of the LTI system both in the continuous time domain and in the discrete time domain. We also saw the two methods of discretization where in the first method we did the approximation while in the second method we consider the input as a piecewise constant signal. Third, we also discuss the importance of the characteristic polynomial and its eigenvalues. So today we'll start with the notion of equivalent state notations. First of all, we'll see the what is the problem statement, and then we'll see the solution or the definition and the definitions of when can we say that the two states equations are equivalent. Consider this network which is shown in the figure where we have three elements. The resistors and the capacitors are connected in parallel in series with the inductor. So all these variables, the resistance, capacitor and the inductor are having the value of 1. Input U is defined by the input voltage and the output Y we are collecting or we are seeing the output as the voltage across the capacitor. Now as we also saw in the first lecture of defining the state variables, similarly there are two ways or there are multiple ways of defining the state variables. So let's see these two set of state variables. So the circuit remain the same. Here in this, let's denote this first figure and let's denote this second figure. Okay, so in the first figure we define two state variables x1 and x2, where x1 is the current flowing inside the inductor in this branch. So naturally the voltage across this inductor is given by the derivative of x1. Second, the x2, which is the voltage across the capacitor. So here you are saying that x2 is flowing inside this branch, which is the resistor. So if I compute the voltage across this resistor, which is equal to x2, and the same voltage would also be across the capacitor. So that's why we are denoting x2 as the capacitor voltage or the current flowing inside the resistor branch. Okay, in the second figure we define the state variables x1 bar and x2 bar, which are basically the loop currents in this first loop and in this second loop. So you can compute the voltages now across the inductor, the resistor and also the capacitor. Right? Now using these two different set of state variables, we can write two different state space representation. By the state space representation we mean the ABCD matrices. Let's denote this matrix A, this matrix B. Similarly, let's denote this A bar and B bar. Right? So if we pay attention to this first set of state variables, we know that x1 dot is given by minus x2 plus u, which is basically we are solving the loop equations for both the circuits by considering the x1 as a state variable and x1 and x bar as a state variable. So here the question arises that given two or more state space equation, when can we say that these equations are equivalent or describe the same systems? Now naturally we see that given a circuit, we have defined two different state space representations. So we know at the outset that these two representations basically describe the same system. Now we'll take the converse problem in the sense given any two representations, any two state space representation, how we can ensure that these two state representation basically describe the dynamics of the same system. Okay, so this is the problem we would address today. So first we'll define this notion very quickly in an informal way. Let's say we have the n-dimensional continuous time LTI system. So first we'll take the discussion of the LTI systems and then we will move towards the LTV case. So we have this state equation given by this x dot and the output equation is given by this output equation. Suppose we are also given a non-singular matrix T which satisfy this equation. So we define a variable x bar is equal to the multiplication of the non-singular matrix T and the state variable x. So let's take the derivative of this part. So we would have x bar dot is equal to t into x dot. So here x dot we will replace by this state equation, the original state equation. So by putting x dot from here to here, we get TAX plus TBU. Okay. Now from here we also know that since T is non-singular, the inverse of this matrix exists, and I can represent X equal to T inverse of X bar. Okay. So again, substituting this X here, we would get TAT inverse X bar plus TBU. Okay. Similarly, we do the same. We replace this X by this X. So we get C into T inverse into X bar plus D into U. Okay. Now you see that this whole matrix, whole multiplication, I can represent by A bar, this one by B bar, and this one by C bar. So in fact, I would obtain that X, that I can represent another state space representation in terms of this A bar, B bar, C bar and D bar, right, for all these relationships. Now let's define this formally. So consider this again, this n-dimensional continuous time LTI systems given by the same equations. So we give first of all we give the definition of the algebraic equivalence, in the sense let T be an n cross n real non-singular matrix, and let we define X bar is equal to T into X. Then the state equation, which is defined by another state space representation A bar, B bar, C bar, D bar, where all these A bar, B bar, C bar, D bar satisfy these relations. Then we say that these two representations are algebraically equivalent, and this equation X bar is equal to Tx is defined as the equivalence transformation. Okay, now the next question arises. If you have two different state space representation, now what would happen to their eigenvalues and also the transfer function? Does the eigenvalues remain the same? And the same goes with the transfer functions. So the equivalent transformations have the same set of eigenvalues and also have the same transfer functions. So we can see quickly the derivation of these two. Let's say we define the characteristics polynomial by delta bar of lambda of this representation, okay, which is given by the determinant of lambda I minus A bar, right? Now if I replace this A bar from this equation, so we get this TA T inverse, and I replace I by T into T inverse. Okay, since the T is non-singular, the inverse exists, and multiplication it or pre-multiplying or post-multiplying with the T matrix, it would give the identity matrix. Okay. Now I rearrange these equations to finally give me this part T lambda I minus A into T inverse. Okay. Now see here, this whole part I can write as the multiplication of determinant of T into determinant of this part into determinant of T inverse, right? But I know that the determinant of T into determinant of T inverse would be equal to the identity matrix. Okay, so finally I would get determinant of lambda I minus A, which is equivalent to the characteristics polynomial of the original state space equation. So if the characteristic polynomial remains the same, then the eigenvalues would also remain the same. Similarly, for the transfer functions, let's denote the transfer function of the representation defined by A bar by the bars. So this is given by C bar Si minus A bar inverse B bar plus D bar. Again, if I replace all these bar matrices into using these equations, I would get this, and after some simplification, finally I got this. You can show, in fact you can show it by yourself as well. So we see that the transfer functions also remain the same together with the eigenvalues. Let's introduce another definition, what we call the zero state equivalence. So in the last couple of lectures, we have also defined what do we mean by the zero state equivalent. So this is a natural definition that two state equations are said to be zero state equivalent whenever they have the same transfer function matrix. Okay, so now we have introduced two definitions. One is the algebraic equivalent, another is the zero state equivalent. So the natural question arises, is there any relationship between the zero state equivalence and the algebraic equivalence, meaning to say whether zero state equivalence implies algebraic equivalence or algebraic equivalence implies zero state equivalence, or they both are equivalent, right? So the first implication is that the algebraic equivalence always implies that the system or the two representation would have the zero state equivalence, right? Because it is the property of the algebraic equivalence that they would have the same transfer function. Okay, and we have defined the zero state equivalent in the sense that they would be having the same transfer functions. So this implication would always hold, right? But we cannot say that the reverse implication would hold, in the sense that the zero state equivalence may not implies that the system would be algebraic equivalence. Okay, so under what conditions we can ensure the zero state equivalent, that the two state space representations would have the same transfer functions, okay, or they are zero state equivalents. So before answering that question, first of all we will introduce the Markov parameters. Let's see. So we know that the inverse of Si minus A is basically the Laplace inverse of the exponential matrix, or the matrix exponential, that is e to the power at. And this e to the power at I can represent as an infinite series of this entity. Okay, starting from I is equal to 0 to infinity. Okay, now I know this property that I can write this the Laplace, or in fact I can write this as the summation of Laplace inverse of Ti by I factorial into Laplace of Ai, right, using the property of the Laplace transform. So first we'll take this term. Okay, so since this part can be, if I take the Laplace transform of the ratio Ti and I factorial, it is basically given by this one. Okay, so putting this back to here, we get the inverse of the Si minus A is equal to this part. So we just replace this part, or let's say to be precise, this part by this part. And since A to the power I is a constant matrix, the Laplace would be the same. Okay. So let's see the transfer function g hat of S, which is given by C Si minus A inverse B plus D. So which I can write by replacing this part by this part. Okay, so I would have D plus summation of S to the power minus I plus 1 into C Ai into B. Since S is a scalar, I can commute. Okay, so all these matrices which are denoted here as D, C Ai, C into A to the power I into B, they all are called the Markov parameters. Now these Markov parameters we can also relate to the impulse response of the system. So we know that g of t is basically given by the Laplace inverse of g hat. So if I just replace g hat by this part, I would get this, and this C Si minus A inverse B can be represented by C into e to the matrix exponential B plus D into delta t. Okay, so if I take the ith derivative both sides of this and this, I would get C into A to the power I into matrix exponential B for all I greater than equal to 1 and t greater than equal to 0. Okay, from which we, so if I take the limit both sides, so this part when t tends to 0, this part would go towards 2i and I would remain this one, okay, which is also the Markov parameters. Okay. So after seeing the definitions of the Markov parameters, we can now answer the question what we have raised in the previous slide, that these two representations, the first given by this one, another is given by the bar matrices, they are zero state equivalent or they have the same transfer function matrix if and only if they have the same Markov parameters, right? That is, d is equal to d bar and c into a to the power I into b is equivalent to their bar counterparts, okay, for all I greater than equal to 0. So this, I think you could, the proof of this result you can do it by yourself. This is pretty much straightforward. Now moving towards to the LTV case, now we know that in the LTV systems all these matrices would be time dependent matrices. Okay, so similarly, first of all we define the algebraic equivalence. So here we define a non-singular matrix as P of t, which is also a n cross n matrix. Now this P of t also assume to satisfy these two property, that the P of t and the derivative of the P of t is continuous for all time t. Okay. Now again in a similar way we define this transformation as x bar is equal to P of t into x. Then we say that these equation is said to be algebraic equivalent to this one whenever all these a bar, b bar, c bar, d bar satisfies these equations, and P of t in that case would be said the algebraic equivalent transformation. Okay. So you can show this by yourself very quickly in a similar way what we have done for the LTI system. That if I put this part starting from this point, then I will take the derivative of this part and the derivative of this I would replace by this one. And similarly you would obtain these bar counterparts. Okay. So now what happens to the fundamental matrix, because we saw that in the LTV case the notion of the fundamental matrix played an important role. So if the two state representations are equivalent, or the fundamental matrix remains same, or they would change. So we have the next result, let x of t be a fundamental matrix of 15. Now this 15 is the original state space without the bars. So then this x bar, which is defined by the multiplication of the transformation matrix into the fundamental matrix of the original state space representation, would be a fundamental matrix of the transform system, basically this part 16. Okay, we can show this result very quickly in the sense. So let's say we know from one of the properties of the fundamental matrix that the derivative of this fundamental matrix is basically equal to a of t into x of t. Okay. So we know that x bar is equal to p into x. So whenever possible we won't be using the time as the argument, so it is implicitly clear that I am talking about the x bar of t is equal to p of t into x of t. Okay. So we know first point that p of t is singular, is non-singular. And since one of the properties of the fundamental matrix that x is also non-singular, so if I multiply two non-singular matrices, the multiplication would also be non-singular. It won't affect the property of the non-singularity. So we are clear that x bar would also be non-singular. Okay. Now taking the derivative of P into X, which would be given by P dot X plus Px dot. Now replacing this X dot by this equation, we would get P A into X. Again, all the arguments of T are implicit, which I can write as P dot plus PA into X by taking X common from the both the terms. Again introducing the inverse, the multiplication of the P inverse in P, which is given by the P inverse in P X, which supposedly should be identity matrix. Okay, so this I can separate both the terms at Px. Okay, and this part we know is given by A bar. If we see the previous slide, that A bar is defined as the multiplication of PA plus P dot multiplied by P inverse. So this term P dot plus PA multiplied by P inverse is A bar, and this we have already defined here, which is X bar. Okay, so it would satisfy that the derivative of X bar is equal to A bar into X bar, basically the same equation, meaning to say that X bar is a fundamental matrix defined by the multiplication of P and X. Okay. The next result says that let A naught be an arbitrary constant matrix, then there exists an equivalent transformation that transforms 15 into 16 with A bar is equal to A naught. This 15th numbered equation is the original state space equation, and 16th is the equation with the bars. Okay, now this is one of the very important results, because what happens here, that this A bar matrix, which is supposedly to be a time dependent matrix, I can replace that matrix with a constant matrix A naught. Okay, so we'll see the proof of this one. So first of all, let xt be a fundamental matrix of x dot is equal to 80 into x. Now if I take the derivative of this part, I know that x is the x matrix is a non-singular matrix, so this x inverse into x satisfy this I. If I take the derivative both sides, I would have the x inverse derivative into x plus x inverse into x dot is equal to 0, right? Which implies that I can express x inverse derivative by this part, and finally minus x inverse into a. Okay. So since because A bar is equal to A naught, which is a constant matrix, because it's no longer a time dependent matrix, so the fundamental matrix would be a matrix exponential. Right? This is what we also saw when we first computed the solution for the LTV system, and then we tailored it for the LTI system. Right? So the fundamental matrix of the transform system is basically given by the matrix exponential e to the power A naught t, and the idea here to replace this A bar t by a constant matrix A naught. Okay. So again, recalling the result what we had seen in the last slide, that x bar is equal to p into x, I can express p of t as the multiplication of x bar into x inverse, where x bar I know that it's the metric exponential. So my p of t is basically the metric exponential into the inverse of x. And then we compute this A bar, which was given by P into A plus P dot into P inverse. Okay. Now here P of t is replaced by this part, and after doing some simplification which you can look more closely, we finally arrive that A bar t is actually equal to A naught. So this is one of the important results in the sense that I can replace the state matrix of the time varying system into a time invariant system. Because for the LTI case we have the state matrix as a time invariant matrix which does not depend on the time. So if A naught is chosen as a zero matrix, then P of t is basically given by the inverse of x, and I can replace A bar, B bar, C bar, D bar by these equations where A naught is my zero matrix. So if this is my original state space representation, the time varying state space representation, I can transform it into this part by using this P of t is equal to x inverse of t, where there is no longer an A matrix. Okay. So every time varying state equation can be transformed into such a block diagram where you can replace the time dependent matrix into a constant matrix. But the most important thing is that the solution, or basically this transformation, relies on the computation of the fundamental matrix. And this we have already seen while computing the solution of the LTV system, that computing the fundamental matrix is quite challenging. The invariance of the impulse response matrix. Say for example, if this gt comma tau defines the original impulse function, the impulse function of the original state space equation, where we have replaced this phi, the state transition matrix, by the multiplication of capital xt into inverse of capital X into tau. Okay, this was the solution of the state transition matrix. So if I use if I write the impulse function or the transfer impulse function of the state space representation given by the bars and replacing all those bars by their counterparts, finally I would have the equivalence with the original impulse function. So meaning to say that the impulse function or the impulse response matrix is also invariance under this transformation.